This is problem 6-26 on page 279. A sign is subjected to a wind loading that exerts horizontal forces of 300 pounds on joints B and C of one of the side supporting trusses. Determine the force in each member of the truss and state if the members are in tension or compression. Now I'm going to draw this system because I think that when the authors made up this problem, I think they made a mistake on the geometry. I don't think they intended for it to be quite so complicated, but it turns out this is not trivial geometry. I actually drew it in SolidWorks because along the way I had slight errors and wondered what on earth was going on. The way they drew it in the book, it looks like that you would just have a very simple 45-degree angle on both sides, and that's not the case. In fact, I've purposely tried to angle this in just a bit to represent the fact that it is different from the left-hand side. But anyway, I don't know what their intentions were, I just know what they actually gave us, and that's what we'll solve. So there's 300 pounds of force at these points, and they did give us some point names. Let me copy those down as well. I don't have it on my worksheet. But this is point A, this is point E, point C, point D. I should say joint, not just point. All these points are joints. And there's some geometry given as well. I guess I'll copy it down. 12 foot from C to D, 12 foot from D on to E, 13 feet between C and B, 5 feet, everything suggesting, between B and D, everything suggesting that they're trying to make it as easy as possible. A 12, 5, 13 triangle is very common. So, of course, this would be 13 feet as well. They gave us a 45-degree angle here, and I think that's all of the geometry that they've given us. Okay. Now, as I went through my solution, I found that I needed some dimensions that I had to calculate. So let me show you how I did this. First of all, I started off with a free body diagram and then quickly realized I needed a little more geometry. So let me just sketch the free body diagram. Said, okay, AX, AY, EX, and EY, as well as the externally applied 300-pound loads, act that way on the truss. Now, I realized that I needed to know information about the geometry over here. I get it that there's 13 feet on this side between BE, but what about the horizontal and vertical components of that side? So I thought, well, what I'll do is try to determine sort of how this triangle is laid out. So I said, okay, if I want the angle here, which would be useful, I could compute it using the angle here, because look, these two are triangles that are back to back, right? They're the same thing. They're both right triangles. So I said, well, this angle's pretty easy, or I mean down here, that's easy to get as well. For whatever reason, just the one at the top kind of jumped out at me. But anyway, that's what I was thinking, so I guess I'll leave them there. This side, you can calculate the angle as the inverse cosine of 12/13, right? Because look, we've got the 12 side here and the 13 side here. It's a right triangle. It's the cosine angle, right? So this angle, I call it whatever you want, theta, it doesn't matter. That's the angle that will be useful. It comes out to be about 22.61986 degrees. It's irrational, I'm sure it goes on forever. But there it is. Well, I suppose it goes on forever. And so what I did from that is I said, well, wait a second. What that means is that if I look at Because what I was thinking of doing was trying to come up with this angle, but I realized this was at an angle, I'd have to get the angle to vertical here, and it would be a big pain. So, well, wait a second, what about if I look at an overall right triangle like this? Because then I know an angle on one side of that triangle. Okay. And notice I know the hypotenuse length from here to here must be 24 feet. So looking at that blue triangle I drew, I know it's a free body diagram and I'm putting geometry on top of it, but we need the geometry. That blue triangle has a hypotenuse of 24 feet. So now I can actually calculate the overall height. Let me continue in blue. And that came out to 15385 feet, and the base came out to about 9.23077. And these are both feet, of course. Okay. So that's one of the dimensions that I really wanted to get, was this dimension right here, 9.23077 feet. And if you take the height, 22.15385, and subtract 13 feet, then you can get this height. And that came out to 9.15385. Now, since this leg's at a 45-degree angle, then that means that this distance is also 9.15385. And these are feet. I keep dropping my units, but all the dimensions are in feet. So you notice this is deceptively, well, it looks like it's simple, but it's not. This is 9.153, this is 9.23. So actually this angle is a little more to the right. I should have drawn it, I guess, farther to the right. So that was the geometry that I had to solve before I could do anything like sum moments about point A. If I sum moments about point A, I should be able to get at EY. EX passes through it, but I needed that moment arm from here to here. Now, in other words, I needed the sum of the 9.153 plus 9.23. So taking that counterclockwise as positive EY causes a moment. Its moment arm is the sum of 9.23077 and 9.15385. That's where I got 18.38462 feet. Minus, well, both 300-pound loads cause a negative moment arm. So minus 300, this lower one, times its moment arm, but its moment arm is 9.15385. Minus 300 times the overall height, 22.15385. So from this, we can solve for EY. Bit of a pain, but it can be done now. And so it comes out to 510. What I'm going to do is just put the reactions right into the original diagram. 510.8787 pounds, and that's EY approximate. It's not exact, but it's close enough for our purposes. If we sum forces in the vertical direction now, that will yield AY. Because think about it, EY and AY are the only vertical components, and therefore AY is actually pulling down, but I'm going to draw it upward and write AY equals a negative 510.8787 pounds. Okay. I don't know why I left it that way, but that's the way I left it. You could just turn the arrow around and make it positive if you want. So that gives me the reactions, at least in the vertical direction. Now notice that AY and AX have to be the same magnitude, right? Because think about it, they sum to act along a two-force member AB, and so they have to sum along the direction of the member. Therefore, AX is like this, but negative 510 point so on and so forth pounds, okay? Now, the reason for calculating this is so that we can calculate the force in member AB. The force in member AB would have to be the square root of AX squared plus AY squared, because notice that these two forces, as I said, have to add to act along member AB. Otherwise, the member wouldn't be stable. And so if you take the square root of the sum of the squares of 510.8787, what you get is about 722.4915 pounds. Now, is that tension or compression? Well, notice the way I've drawn it is opposite to reality. In reality, the forces, the reactions from the ground onto the truss are actually pulling down this way. So that is a tensile load. So we've already got the force in member AB. I guess I'll cross them off in red if red works. There we go. So we've got the load in member AB. Now we're supposed to use the method of joints to work this problem. Since I've got all the geometry over there, I don't need that angle anymore. I think I'll erase my three-body diagram. And really what I've done here is I took a free body diagram of pin A and said, well, wait a second. AY, AX, AB is something like this, and so AB acts, you know, there's a lot of opposites here, but that's how I came up with this result, okay? So you can sum forces in the horizontal, vertical direction if you want, but that's what I did. So, if we look at our, well, I shouldn't have erased the free body. I had AX and EX, and I haven't dealt with EX yet. Remember there are, I'll just draw it down, or draw where they were. So in reality, AX acts this way, 510 point, so on and so forth. So notice that 510 is less than the sum of these two. And therefore EX has to help out. But EX won't have a whole lot. It'll be what? 300 plus 300 minus 510 points, so on and so forth. What? 87, 87? And so EX is fairly small, but it's not zero. EX, if I were to draw it here, it's going to act to the left, but if I draw it to the right to be consistent with what I've done with AX, then it would be a negative, whatever this number is. Well, that number is 89.1213 pounds. Okay. So there are the rest of the external forces, the external reaction forces. All right, probably the next easiest point to go to is point C at the top. Because if you look at point C, there's a 300-pound load acting at the top. And then there's force in member CB and force in member CD. Now the angle here, we know, is theta. I did erase it. I guess we still need it. Maybe not. We might be able to use, well, I ended up using the angle, so we'll just leave it. So if we sum forces in the horizontal direction, we'd have 300 pounds from here plus CDX equals 0. And so CDX must be the negative 300 pounds. Okay? But if we were trying to relate CDX to CD, how would we do it? Now let's see, CDX is a component that moves along like this, and that's not so easy to see. Let me erase CB for just a moment. If I want the horizontal component and I know the angle, you see the right triangle here? Right, we know this angle theta, and so this is the sine side in order to get CDX. So basically, if I take CD and multiply it by the sine of the angle theta, then I should get negative 300 pounds. So if I take CD and solve for it, divide by the sine of theta, where theta is at 22 point whatever degrees, I will get CD. Now CD comes out nice and round. CD comes out to, you know, I guess we could put the force on the member. So 22.4915 tension. Anyway, it was CD that I just solved for. It comes out to a nice round negative 300 over sine theta negative 780 pounds. And since it's negative, what that means is that it's compressive. So let's just do it that way. So remember that angle I had, 22 point whatever degrees. That's what you use in the sine function. All right, well that's CD. Well, what about CB? Well, we can sum forces in the vertical direction. And that would be what? Negative CB minus CDY. And so CB must be the negative of CDY. But CDY, to get that, we just take the cosine piece, right? The cosine of theta. Since we know CD now, we can calculate CB. CD is 780, but let's be careful here. It's a negative 780 because it's compression. Cosine of 22.61986 degrees. Now this number comes out nice and round as well at 720 pounds. So the force in member CB came out positive and therefore is a tensile load. Whereas of course CD is compressive. And that should make sense. If you think about holding this and pushing this, you're going to compress this member, expand this other member. That makes a lot of sense. So we got quite a bit of mileage out of just point C. What about point D? What could we do with it? Well, point D you should recognize as a point that could have zero force in one direction. In fact, that's what it has. Notice that CD and DE are aligned. Therefore, any force in BD would cause this point to move. So BD has to be zero. Summing forces along this direction, what you would notice is that CD and DE are equal. So we just found that BD is a zero force member, and we just figured out that DE has a 780 pound compressive load in it. Just by drawing the free body diagram and thinking of the sum of forces in our head. Okay, so that's pretty straightforward. So point D was fruitful for us as well. Now we should be able to tackle point B. Let's make a free body diagram of point B. And for point B we had BD, but that was zero. We have CB, straight up. Notice I'm drawing all of these in the positive direction. We have, or in, I should say, a tensile direction. BE, AB, but there's also an external 300 pound load at this joint, which is what? Joint B. Okay. So, with that in mind, if we sum forces in the horizontal direction for this joint, we'd get what? Well, negative ABX, the horizontal piece of AB, plus BEX, horizontal component of BE. BD we don't have to worry about, CB is only vertical, plus 300, external load, equals 0. All right, so the horizontal component of AB, remember AB is a 45-degree line. So its horizontal component would just be AB over root 2. How about BEX? Well, BEX down here, and notice we know the height of that triangle. I shouldn't have made that a solid line. We know the height, that's 9.15385 feet. We know the base, 9.23077, and we know the hypotenuse. So if we want BEX, we should be able to write it pretty easily. Let me do it this way. Let me solve for BEX. I'll just leave it where it is. Take the other terms to the other side, so AB over root 2, flipping the sign, minus 300, flip that sign also. But BEX, if I want the horizontal component, I just need this side over the hypotenuse, 9.23077. So I can erase this and say BE times 9.23077 divided by the hypotenuse of 13 feet. And so now all I have to do is solve for BE. Of course, plug in AB as well. We know that AB, I've drawn it as tension. It is actually a tensile load, 722.4915. I went through a little bit of math to solve for this. Obviously, all you got to do is take this and multiply it by 13 over 9.23077. That takes care of that bit. And now we've got BE. Plug it into your calculator and you'll get the number. It's BE is 296.9874. And it came out positive, so that tells me, let's see, BE, here it is. 296.9874. Came out positive, that tells me this is in tension. I think that's it, right? Because we've got, let's see, 1, 2, 3, 4, 5, 6, yeah, 6 members and 6 numbers. But notice there's one point that we have not considered yet, or one joint, and that is joint E. Joint E should be available as a check so that we can verify that what we've done so far makes some sense. I guess we could have summed forces in the vertical direction as well, but for the last point, point B. But I'll just use point E as a check. Let's see, point E has DE, it has BE, it has EY, and EX. Okay. Summing forces in the horizontal direction, we get the X component of BE in the negative direction, the X component of DE in the negative direction, plus EX. Does that come out to 0? Have we solved this problem? This was about the point where I figured out I'd made a mistake. And I had not considered the fact that this leg was not at 45 degrees. I'd gone through the whole solution and didn't realize my geometry was off. It was off just a little bit. The numbers weren't coming out. But sure enough, this problem was set up to be a little more difficult. Anyway, BEX, how can I write that? Well, negative BE, but I only want the horizontal component. Where's BE? It's right here. Horizontal component, 9.23077 over 13. Okay, 9.23077 over 13. Minus DEX. Well, where's DE? DE is right here. If I want the horizontal component of it, how would I get that? Well, remember this is part of a larger triangle, right? It has the same angle as the larger triangle. So if I want the horizontal piece, all I got to do is take 9.23077 divided by the entire hypotenuse of 24 feet. So 9.23077 over 24 plus EX, but EX is a negative thing. So notice I've been consistent in my direction. And so it's a negative 89.1213 pounds. My question is, does this in fact come out to 0? Well, we know what BE should be. It's 296.9874, and we know what DE should. Now be careful, this is tension, so I plug it in positively, right? DE is compressive, so I've got to plug it in negative. So negative 780 for DE. Can't seem to make it 0 today. There we go. So if you plug all of this into your calculator, sure enough, you get 0 from this. You just have to take my word for it or try it yourself. We can also sum forces in the vertical direction to check and make sure everything's okay. We'd have EY plus BEY plus DEY, and it should come out to 0. That's what we're checking. And so EY is 510.8787. BE, well, BE, I'll write down the magnitude of all of BE first and then take its component. BE is right here, 296.9874. But I don't want all of it, I just want the Y component. So to get the Y component, that'd be 9.15385 over 13. Okay, so that takes care of EY, BEY, DEY. Again, I will take all of DE, which is a negative 780. Right? Remember, I've drawn DE as a tensile thing. It's actually compressive, so I have to plug in negative. But I only want the Y component. Remember, it's part of a larger triangle, so I need the overall height, which I unfortunately have erased, but it's 9.15385 plus 13. So it comes out to what, 22.15385? So 22.15385 divided by, let's see, so that's the vertical component of the larger triangle, divided by the hypotenuse, 24 feet. And if you plug this into your calculator, you also get 0 from all of this. So at this point, I was reasonably satisfied. Of course, I've rounded them off, so I got very small, like 10 to the negative third or fourth, something like that. I don't remember. 10 to the negative fourth, I think. And that's one of the reasons probably I carried so many decimal places through this. Because this angle here is not far from 45 for BE. But it's enough that your numbers come out inconsistent. It was, like I said, at this point or a little bit before that I realized something was wrong. And so I ended up pulling out SolidWorks and drawing this because they gave us enough information so that I could draw it. And sure enough, I measured the angle and it was not 45 degrees. But anyway, there's the solution to 26.